Welcome to the SEI podcast series, a production of Carnegie Mellon University Software Engineering Institute. The SEI is a federally funded research and development center sponsored by the U.S. Department of Defense. Today's podcast is available on the SEI website at sei.cmu.edu/podcasts. My name is Suzanne Miller. I'm a principal researcher here at the SEI. Today, I'm very pleased to introduce you to Drs. Carol Woody and Rick Kazman, my colleagues. We're here today to talk about a tool that they've developed for identifying vulnerabilities and other issues in software architectures. But first, a little bit about our guests. Dr. Woody is the technical manager of the cybersecurity engineering team of the CERT division. Her research focuses on defining, acquiring, developing, managing, measuring, and sustaining secure software in very complex network systems and systems of systems. That's a lot of stuff. Carol's very busy.
Yes.
As for Rick, in addition to his research here, he's also a faculty member at the University of Hawaii. At the SEI, his research focuses on software architecture, software engineering economics, design and development tools, and software visualizations. Welcome to you both. Thank you for joining us.
Thanks, Susie.
So let's talk about your decision to focus on software architecture as the root cause of vulnerabilities. So we have lots of focus on code. We have lots of focus on different aspects of trying to find out where the vulnerabilities in the system are. You decided to focus on software architecture. So what is about that? Why did you decide to go there?
Well, let me give a little background. When we look at cybersecurity engineering, most folks think of vulnerabilities, and typically those are found in the code, and those are later in the life cycle. But there is a major block of design weaknesses that are implemented in the system and are very hard to change later on.
Sure.
In terms of overall problems, design weaknesses represent probably about 40% of what we've identified as general weaknesses that you're dealing with code and design. However, when we look at what experts have identified as the top 25 problems, design weaknesses represent over 75% of those.
Wow.
So this is an important area. It's a difficult area because the way that we typically think about security, we think of it as completed systems and analyzing its overall security. Here we have to think about what is the system doing, how are we building it so that it doesn't have those problems when we ultimately field it.
And as we all know, the later that you find these problems that were introduced in an earlier phase like design, the harder it is. This is part of the difficulty. So if we can find design weaknesses in the architecture and fix them then we have a much easier time all the way down the life cycle.
Well, that's what initiated discussions that Rick and I were trying to look at to say, what can we do? And he'll give you a little more details about the tools he's starting to work with, but he had some pieces he was looking at architecture in general for flaws. And we said, okay, how can we structure those in a way to find these major problem areas that we're trying to explore?
So that's a big part of the challenge is we have all these architectural patterns, and those patterns are designed to meet certain functional and non-functional requirements that we have. But the awareness of how different patterns affect security may not be as great as it needs to be within the architectural community as well as the design and implementation community. Is that fair to say?
Yeah, and more than just the patterns, the ways in which people get them wrong. So
good patterns gone wrong.
or even patterns that they should have used but didn't.
Okay. All right.
Patterns they thought they did.
They thought they used, but they really implemented something else that was not as effective and could have introduced a vulnerability or a weakness. So you tend to talk about weaknesses rather than vulnerabilities. Is that a purposeful word choice?
Well, weaknesses tend to be the way we build things that allow vulnerabilities to occur.
Okay. So they're more of the root cause
exactly.
of a
So
vulnerability.
As we're pushing up earlier in the life cycle, we don't really have tools that can pinpoint and say this is a vulnerability.
Right.
It's more of how the pieces are being glued and designed together.
Okay.
And I think as Rick gets into some of the details about what we're doing, you'll find that we don't really have ways of pinpointing in the designs what will cause a vulnerability, but we can certainly begin to narrow the area we need to look in
Okay.
to help us better
Provide focus.
and allow us to reduce the amount of deep dive we have to
Right.
do to find problems.
Because that's expensive, right? Trying to
and
look
money.
across a broad spectrum of potential weaknesses at a deep level is a very expensive proposition. So let's talk about your approach. You've got an approach that you've developed in collaboration with Drexel University, from what I understand. And so that collaboration has resulted in a structure that seems to have some promise in this area. So tell us about it.
So this collaboration began in late 2009. So we've been collaborating about 5-6 years. I've been collaborating with Professor Yunfang Tsai at Drexel and some of her PhD students.
Okay.
And if we just back up, before that time, we had done a lot of work at the SEI in architecture analysis and developed a number of methods. And we got a lot of leverage out of those methods. We could go a long way to finding potential risks, but they tended to be, what do I want to say? The risks that we identified tended to be broad brushes. And what we wanted was the ability to zoom in a little bit closer and try and find the architectural weaknesses or flaws, or we sometimes call them hotspots, that are the likely sites of future headaches.
Right.
To use a non-technical way of describing this.
But that describes what's going to happen if one of them gets implemented.
It's going to be headaches.
Yeah.
So what we've developed over the years is a design representation and an associated set of tools that allow us to reverse engineer an existing code base, extract architectural information, design information, manipulate that information in interesting ways, and then analyze that manipulated form of the information to find architectural flaws.
Right.
And this is something that we were never able to do before, and this is all automated, which is great, because all the techniques we developed before were completely manual, which meant it's very labor intensive, doesn't scale up very well.
So 1993, I attended a software engineering symposium that the SEI sponsored, and one of the researchers, one of our colleagues, Dennis Smith, was talking about reverse engineering. I went to his tutorial on reverse engineering, and the big thing there is this would be so wonderful if we could automate this, because to do this by hand, to do this manually, is just takes a huge amount of resource, almost impossible in that time frame. So you've actually made good on one of Dennis Smith's promises for the future, was when we can automate this, we can do something with it.
That's right.
So that's wonderful.
And so we've actually crossed that bridge pretty successfully at this point.
So what are some of the highlights of the approach itself, especially for people that are architects in our audience? What are some things that would help them understand what it is that this actually does for them?
Yeah, let me actually explain that by talking about the tool chain that we've developed. So on the left side of the tool chain are all the inputs. And the inputs are things that every project has. Every project has source code, or every mature project, let's say, has source code. Every project uses some kind of revision control system, Subversion or Git or something like that, to manage commits and manage releases and so forth. And every mature project uses some kind of issue tracking system, like Jira, let's say, to manage their bugs and changes to the system. So all of these are inputs. And so it's more than just reverse engineering the code, which is the kind of Dennis Smith vision
dream
of the world.
Yeah,
the dream of 1993. And we've now realized actually there's a lot of information in these other artifacts that augment just that code view. So we reverse engineer the code, and right now we're primarily using just a commercial reverse engineering tool called Understand. But we could, in principle, use any reverse engineering tool that will tell us about the basic facts of the system. File A inherits from file B, or file A calls file B, or file A depends on file B, or aggregates, or anything like that. Any system that that gives us that information we could use. In fact, we've done a version of this system where we sucked in information from enterprise architects, so we can even do the analysis on designs. So this excuse me. This outputs a set of dependencies between files. So you can think of those as triples, as file A, file B, and some relationship between them. And based on that, we generate a big matrix. It's a design structure matrix. So that's just a square matrix where the names of all the rows are the file names. And on the columns, we have the same set of file names in the same order. So it's a square matrix. The diagonal is the self-dependency or self-relationship. And every cell in the matrix represents some dependency between file on the row and file on the column, or no dependency if there isn't a dependency between them. So we've got that DSM, that design structure matrix, and we can analyze and manipulate that. And what we do is we cluster it using an algorithm we've developed. It's called the design rule hierarchy algorithm. So a design rule would be something like an important interface or an important class in the system. So my favorite example is if you're using abstract factory in your system, you're going to have a lot of other files that depend on that abstraction. So there will be classes that implement the abstract factory interface, that inherit from it, that depend on it, that use it, that aggregate it. And so that abstract factory representation is a design rule, and a lot of other files will depend on that design rule. So what we do is we cluster the architecture in terms of dependencies. So at the top are all of the leading classes, the most important design rules in the system.
And most important in terms of the most dependencies.
Right.
Others using that.
Exactly. The classes or the files that lots and lots of other files in the system depend on. And then, so we would cluster that into a layer, those files into a layer. And then the layer below that would be the files that directly depend on those files. And the layer below that would be the files that depend on layers 1 and 2 and so forth. So it's a hierarchy. And in this way, we can cluster the entire system. And then we can analyze that hierarchy, and we can run all kinds of interesting analyses just based on the structure. So for example, we can find cycles of dependencies as a pretty simple example. So if file A calls file B, B calls C, C calls A, that's almost always a bad thing. Because when you change A or B or C, you don't really know what the ripple effects, and these cycles can be a lot more than 3 files long.
That can be a very large circle, not a small.
It could be a long cycle and a lot of non-local,
not easy to see
not easy to see subtle changes that can happen when you tweak one file. Did you want to make a point?
Well, I was just going to point out that that's something a programmer can't easily find. Because you're looking at millions of lines of code. How do you then determine how
And
these pieces
typically,
fit together?
you're working on this piece over here, and this is C, and there's D, E, all the way back to A that are not part of what you've been asked to deal with. So
And they may
you may never see them.
by other people.
Sure.
So, yes.
So that would be an example of an architectural flaw or a hot spot. Another example would be what we call improper inheritance. So if you have file B inherits from file A, but A depends on B. And we actually see this in large numbers of systems, and you think that's crazy. That violates, good design principles. And the response to that is yes, and yet you see it all the time. And it's essentially what Carol said. It's so easy as a programmer to just insert a dependency. Oh, I'm just going to call that method from this method. And you're not thinking about design at that point. You're thinking about getting the job done.
Yep.
And so these problems just creep into a system. They're like rust. They just accumulate. Every system has them, and they get worse over time.
And this is one of the reasons the revision history is important, because there could be points at which that was not an issue, and then all of a sudden something gets introduced in a revision that changes the relationships that might have been positive before, but now create a dependency that's inappropriate.
So let's actually look at that. So we also grab the revision history. So we would grab, let's say, a SVN log, and we would process that. And if you think about the commits in a revision control system, those commits are like a kind of dependency. When file A and file B are committed together, there's some reason why they're committed together, because they both needed to change to fix some bug or
it was
to
perceived
add
that they
some
both
feature.
needed to change.
Right.
Yeah.
So we call that a history relationship.
Okay.
They are historically related.
Okay.
And so we can build a history DSM, a history design structure matrix, where, again, all the files on the rows, all the files on the columns, and every time they change together, we put a mark in that cell. And
then can I look at how are my history relationships reflected as actual relationships in the structural DSM?
Bingo.
Yes. All right.
So that's another kind of architectural flaw. So when you get files that have a no structural relation, but they consistently change together,
there's an implied
in
relationship.
History, there's something going on there. Yeah. So we looked at one system recently which changed the notion of time in the system. So previously it had measured time in seconds, and then at some point they decided they had to measure time in milliseconds. And so what happened was lots and lots of files had to change.
Yeah.
That information was not modularized anywhere. And so it meant every place that knew about time had to change.
Yeah.
So we call that a modularity violation. It's a modularization that they should have done but didn't.
Right.
And as long as they continue to not modularize the notion of time, every time something to do with time changes, you've got to find all the places that might have to change and make commits.
And this is a great example of say in the first 20% of the system modernization, I make that decision. If I don't modularize it, then I've got all these other design elements coming behind that nobody knows that we've done this change. Yeah. So I'm still writing things in seconds because that's what my spec says to do. Yep. But then somebody's going to have to come afterwards and change it to milliseconds and everything else. Oh yeah, that headache.
So we sometimes call these shared secrets.
Yeah. Yeah. Yeah.
Right?
Okay. Yeah.
And they're bad. They're always bad because you rely on tribal knowledge, basically, for the changes to be done correctly, and that breaks down pretty easily.
Sure.
You know, Joe's the guy that knows this, and Joe's away, Joe's on vacation, Joe's sick, Joe's left the company.
So all the architects that are listening to this have got to be very excited about this. So, but they're also going to want to know, what kinds of testing have you done to sort of validate that this provides utility beyond what an architect would normally do in their own analysis?
Yeah, absolutely. So the third piece on the left there is an issue list. So what we can do is we can grab the issues from your favorite issue tracking system, and those are typically classified as either bugs or changes. And we can associate those with every file in the system. Right. And what we see is once we've built these DSMs and we've analyzed them, we can now look at the correlation between the places that we can find flaws.
Okay.
And the rate of changes, the rate of bugs, the rate of churn, in other words, the number of lines of code that have to be committed to fix those bugs and to make those changes. And what we see is incredibly high levels of correlation. So basically, the greater number of architectural flaws a file participates in, the more bugs it experiences, the more changes it experiences, and the more lines of code need to be committed.
And every time you do that, you have potential unintended consequences.
Absolutely, because people typically...
It's an amplifying cycle.
People typically have no clue that these flaws are there. Right. They just know that they're swatting bugs.
Yeah.
And they're dealing with the symptoms.
And they're dealing with the local effect. They're not... They have no way of understanding that there might be a global effect.
Yeah, so if you've got a beehive in the corner of the room and a bee comes by and you swat it, the hive's still there. Yeah. And it's going to just generate a steady stream of bees until you figure out where the problem's coming from. And that's basically what's going on in most software projects.
Okay.
So we can detect these problems, we can identify them, categorize them, we can rank them according to their severity. We have a GUI which allows you to visualize these DSMs and run the various analyses and manipulate them and look at
This has really come a long way since 1993.
It's come a long way.
So if I'm a program manager, an architect out in the world, government, industry, how do I make use of this? Where is it available? What have you written? Where are the tools? All that kind of good stuff. How do I get my hands on it?
Sure. So right now, the software is being licensed by Drexel. They make it available. You ask them. Certainly for academics, it's free. Otherwise, they might want some kind of license agreement done with them. But they've been quite open about sharing that. And
well, we're working with DHS right now to set this up so that it can be available in their software marketplace.
Oh, okay. So that would be a government source.
Yep.
Right.
Excellent.
And so that if you can upload your code, not everybody can, but if you can, then you can run this tool suite against it there.
Okay. Excellent.
Yeah. So that's all being packaged into a virtual machine that we're giving.
It's consumable.
Yeah, we're giving them, and then you can just run your code through this tool chain.
So what's next for this? I've got all these things ripping off in my head about different ways that you might want to take advantage of this. Where is your research going, both of you, Carol and Rick, in terms of taking advantage of this?
Well, we want to leverage this to see can we pinpoint where the security hotspots are.
Wouldn't that be nice?
So that, you may have a lot of architectural issues, but can we get the subset of security issues that are really going to be weaknesses that need to be addressed early?
Okay.
And that's what some of the more recent research we've been analyzing is helping us do.
Yeah.
Excellent.
So we've looked at probably about 150 systems we've analyzed using these tools and this technique, but we've looked specifically at security for probably 10 to 20 systems, and what we found is exactly the same patterns, which is to say the greater number of architectural flaws a file is implicated in, the greater number of security bugs it experiences. So design flaws don't care. Right. They're going to make everything worse, and
security is one of the things they're going to make worse. Right.
So we think this really helps let's say a quality assurance person or a testing person or a security expert figure out where to spend their assurance dollars, where to try and refactor or analyze or test more heavily.
Okay. All right.
So that's kind of our current thrust.
Well, I'm not at all surprised that this is very exciting work, because everything I've done with Carol and Rick in the past has always been things that give us some important insights, and I think this falls right into that. I would encourage all of our listeners to try and take advantage of this, especially if you've got a legacy system that needs to be analyzed this way. So I want to thank both of you for making the time. I know that Rick comes from a long way away, and so does Carol, to do this, so I really appreciate it. Rick recently gave a talk on this work, Locating the Architectural Roots of Technical Debt, at the 2015 Saturn Conference. And to view that presentation, as well as other presentations from Saturn, you can go to our Saturn website at www.sei.edu/Saturn/2015/video. That'll get you to his video explicitly. As always, we will provide links to these kinds of resources in our transcript, and this podcast is available on the SEI website at sei.cmu.edu/podcast. And if any of you in our audience have any questions, please don't hesitate to contact us at info@sei.cmu.edu. Thank you for watching.